In this video, we're going to actually implement some of the things that we looked at in the previous video where we defined what a rational function was and how to find the asymptotes and wholes. And in this video, we're going to take a look at a number of different rational functions, and we're going to be able to find the domain, okay, which we've been able to do all semester. But then we're also going to take a look and find the horizontal asymptotes, the vertical asymptotes, if they exist, and then where the wholes exist, if any, for the function. So we have this function x over x squared plus 9. And so what we're going to do first to find the domain is we're going to set x squared plus 9. And we know that the denominator can never equal 0 for the domain. All right, so remember, for domain, we look for dividing by 0 or any roots. If I were to solve this, x squared would not be equal to negative 9. And then we would take the square root of both sides. And so x would be equal to plus or minus 3i. All right, because remember, when you take the square root of a negative, it's imaginary. And so what that means is that there is no domain restriction. Okay, so that means that there is no domain restriction. And if that's the case, then the domain is all real numbers. Okay, so if the denominator never equals 0 and there's no radicals or anything of that nature, then we don't have any, we just say that the domain is all reals. Right? Second thing, find the equation of the horizontal asymptotes. So that's where we take a look at the degree of the numerator and the degree of the denominator. Okay? Now, the degree of the numerator is equal to 1. The degree of the denominator is equal to 2. Okay? And so if that's the case, then we go back up to our rules and we notice that the degree of the numerator is going to be less than the degree of the denominator. Okay, so that's what we look at. And so going back up to these rules, if the degree of the numerator is less than the degree of the denominator, then y equals 0 is going to be a horizontal asymptote. Okay, so our horizontal asymptote occurs at y equals 0. And so next thing we're going to do is we are going to find the vertical asymptotes. Now, the vertical asymptotes are actually really close to what the domain of the function is generally. Okay, and so all we're going to do is we're going to set the denominator equal to 0. Right? And remember when we tried to solve this, we got that x was equal to plus or minus 3i. And if you ever get an imaginary number, that means that those asymptotes don't exist. Okay, so we would say that the vertical asymptotes do not exist. Okay? And then finally, the last thing we're going to do is we're going to find the wholes. To find the wholes, we would just go through and try to factor the numerator and the denominator. Okay, so we would have x over x squared plus 9. And so notice that these are both prime, meaning that they can't be factored. And so if there's no common factors, that means there are no wholes. Right? Now, the last thing we'd like to do is we'd like to graph this just to verify. Okay, so if we go on the graph of this, and let's take a look at the graph, and let me reset this. Or maybe, okay, there it goes. And we have y equals x over x squared plus 9. And then notice that this function never has a vertical asymptote when I zoom out. Remember something else that we had was we had y equals 0. Okay, so let me plot that line just to show you what that means. And what that means is as x is approaching infinity or negative infinity, that this function is just going through and getting closer and closer to that number, but never really reaching it. Okay, so that's what our horizontal asymptote is. A secondary example, and what I'm going to do really quickly is let me change the function and make this into a -3, okay, just so that way it works. So in reality, let's use this function. G of x is 3x squared over x squared minus 2x minus 3. All right, first thing we need to do, we need to find the domain of the function, all right, which means we're going to set the denominator not equal to 0, just like we did in the last video. And so by factoring, I wind up with x minus 3, x plus 1. right? And so that means that x minus 3 cannot be 0, x plus 1 cannot be equal to 0, and so that means that x cannot be equal to 3, and x cannot be equal to negative 1. And so if we write the domain of the function in interval notation, we go from negative infinity to negative 1, union negative 1 to 3, union 3 to infinity, since x can neither be negative 1 nor 3. That's going to help us because that's going to help us to be able to find the vertical asymptotes, okay, a little bit. So next thing we're going to do is we're going to try to find the horizontal asymptotes. So remember, what we do is we take a look at the degree of the numerator and the degree of the denominator. Now, notice that the degree of both the numerator and denominator are both 2, right? And so the rule is if if it's the same degree, then what you do is you take a look at the coefficients and you divide those out. So y would be equal to 3 over 1, okay, because that's the coefficient of the x squareds, okay? So we don't worry about anything else other than the x squareds. And so that means that there's going to be a horizontal asymptote at the horizontal line y equals 3. Okay, so let's stuff that in our back pocket. So here's our domain. Here's our horizontal asymptote. For the vertical asymptotes, first what we should do is we should see if there's any holes, okay? Because sometimes what happens is the holes eliminate any vertical asymptotes, okay? So I'm going to actually go backward and see if I can find any holes. So I have 3x squared minus 2x minus 3. And what I need to do is I need to factor both the numerator and the denominator. And then once I factor, then what I'm going to do is see if there's any common factors. And remember, we already factored the denominator before. And notice that there's no common factors. Okay, so there are no common factors, which means there's no holes. But that can help us to be able to find the vertical asymptotes. Okay, so the last thing I'm going to do is I'm going to figure out where the denominator is equal to 0 in the reduced function. Okay, so once I reduce the function, if I can, okay, then what I'm going to do is just set these factors equal to 0. And we already know that this one produces x equals 3, and this one also produces x equals negative 1. And those should be the vertical asymptotes, okay? So now if I could cancel something, okay, that would not be a vertical asymptote of the function. Okay? So let's go ahead and graph this just to see whether everything jives, okay? Just to make sure that this is the domain, this is our horizontal asymptote. And what I'm going to do is I'm going to plot the function and the asymptotes on the same graph. Okay, so remember we had 3x squared, and then we had x squared minus 2x minus 3. Okay, so here's our function. And you probably remember that we had y equals 3 as a horizontal asymptote. And check it out. It looks like the function is going towards that 3. Okay, if I zoom out even more, it becomes more apparent. Okay, and that's how you can check to make sure you're right, is if this function kind of starts to blend into that line. Okay, now remember, it'll never touch that line, but it gets closer and closer. Okay. Other asymptotes that we had, x equals negative 1. Okay, and you guys can see that, again, this function is getting closer and closer to that line as x approaches positive infinity from the left and negative infinity as x approaches negative 1 from the right. And then the last asymptote that we had was x equals 3. All right, so there we go. That's this line. Okay. Now, later in this section, what we're going to do is we're going to be able to get a really good illustration of this graph without necessarily having to use a graphing calculator. Okay. And the steps that I just showed you, those are going to be a lot of what we do. Okay. All right. So in the next video, we're going to take a look at a couple more examples of being able to find asymptotes, domains, and then also the holes for these rational functions.